easy ones and maybe a few that are a little bit more complicated. We're going to start out by looking what's on the left-hand side of the reaction equation and adding up all of the moles of atoms that make up all of the reactants. So normally what I like to do is to put these out separately, list them. And on the right-hand side, I like to make the same list. And I like to keep them in the same order so that you can keep track of what's going on just looking from left to right. If I'm looking at this first example, you see on the reactant side, all I have is 1 mole of silicon. And I notice that in that molecule, I've got 4 moles of hydrogen. But when I look on the product side, I have 1 mole of silicon, which is great, those are balanced, but I only have 2 moles of hydrogen gas. So when this reagent decomposes, I need to produce the same number of moles of each species that came from the reactant side, right? So instead of writing all of that down in words, what we're going to do is we're going to balance the equation with coefficients. So those big numbers that you see written in front of the species, those are the numbers that we're going to put on these little lines. And so in order to balance the hydrogens, because it looks like the silicons are all set, I can't take 2 moles of hydrogens away, right, from the reactant side. I can only add, in this case, to the product side. So in order to make that 2 a 4 to balance the hydrogens, I'm going to put a 2 in front of the hydrogen gas. That's only going to change the number of moles of the hydrogen that I see on the product side. And so if you look from left to right now, I have balanced silicon, which was already balanced when we got the thing, right? So we didn't have to do anything. And then now the hydrogens are balanced because you've put a big 2 in front of the H2 on the product side. So this is a pretty easy one, and you probably didn't have to make the list in order to balance that. Sometimes the list is nice because there's a lot to consider. And on occasion, you'll get something gnarly that has, for example, an oxygen in it. Oxygen can sometimes be a real pill when it comes to balancing equations. And we'll try to do a few of those where the oxygen is a pain in the neck and a couple of examples where it isn't. In the next equation, instead of just balancing the moles of atoms or the moles of each species, I also wanted to impress upon you the fact that we have to worry also about balancing the charge. And if you looked on the reactant side, we see that the total net charge of everybody in the pot is positive 3, as written, right? So we have the ferric ion, and then we just have solid zinc. And on the product side, if you add up all of those charges, then the net charge, right, over there is positive 4. So positive 3 does not balance out with positive 4, so we have to fix this. So there's a quick and dirty way to do this. You can just take the lowest common denominator for your odd and even, species. You can look right at the iron and say, well, it's positive 3 on the left, it's positive 2 on the right. The lowest common denominator is 6. But you have to be careful about that because your other species on the product side also has a charge. I think it's actually easier to sort of sit back and think about what's going on. If you look on the left-hand side of the reaction equation, we have the ferric ion, so iron plus 3, and then just zinc 0, right? So zinc has neither gained nor lost any electrons. It's just zinc 0, right? So there's nothing happening there. But if you look at that iron with a positive 3 charge on the reactant side, and then over on the product side, something has happened. You haven't, transmuted the iron. We still have iron. It's just that it's in a different oxidation state. So what have we done? Well, we've taken it from iron 3+, and we have given it an electron, and it has become iron 2+. It's now missing 1 less electron than it was before. And so you're sitting there going, well, how did that happen? Okay, now look at the other half of the reaction. What happened to the zinc? Overall, the zinc has gone from 0, so there's no charge, right? So it has all of its electrons. and it doesn't have any extras, right? So just zinc 0. And you've taken that and you've brought it over to zinc positive 2, meaning you have taken electrons away from the zinc. You have oxidized the zinc. That's what actually happened to it. So if the zinc lost electrons and the iron gained electrons, and they're all hanging out together in the same reaction pot, what do you think happened? Well, we probably transferred electrons from the zinc to the iron. And if zinc lost 2 electrons, and each of those iron ions gained 1, then we must have reduced, that's what that means, right? When you give an electron, you are reducing that whoever you gave it to. So the iron is actually being reduced. And so in order to take 1 electron away from zinc at a time and give it to iron, but then end up with a positive 2 charge on zinc, we must have reduced 2 of the ferric ions. And if we reduced 2 of the ferric ions, we have produced 2 ferrous ions. So now, okay, we have balanced the iron in terms of the number of moles, right? But did we balance the charge? Because we basically just talked our way through this. We didn't really add charge together, or did we? So let's look. On the reactant side, the zinc is still 0, right? But if we're going to take 2 of those ferric ions and each one has a positive 3 charge, the net charge on the left-hand side is positive 6. Now, okay, go over to the product side. We've got zinc, which was oxidized, so zinc with a positive 2 charge, and we have 2 ferrous ions, and each of those iron ions, right, is positive 2, but there's 2 of them. So I've got 2 times positive 2, which is positive 4, and if I add that to the positive 2 on the zinc, I get a positive 6. So now, not only are all the charges balanced, but all of the moles of the species are balanced as well. And we did that by talking our way through the actual process. Zinc has lost 2 electrons, but the thing it lost electrons to only gained 1 at a time. So that thing we needed 2 of. That makes sense? So it's like when we were making our ionic compounds and we were like, we want to balance the charge in the one compound itself. We want to make sure that, okay, we're balancing out, the positive 3 and the negative 2 or whatever. We're doing the same thing, only this time instead of making one salt, we're balancing a whole equation. So there's a couple of different ways that you can approach that. I think it's easiest to just talk my way through it and see what actually happened. Okay, so let's move on to the next example.